Hey folks, as promised in this video, we're going to talk about moment of inertia for extended objects. In the previous video, we talked about moment of inertia for point masses. So what do I mean by extended objects? So let's say I give you a meter stick. So here is the meter stick. And I tell you that you are going to take it and spin it about that axis. So like the left side is coming out of the page toward us, and the right side is going into the page away from us. And I ask you to calculate the moment of inertia of the meter stick as it spins about that axis. Well, it's not a point mass anymore, okay? And you can't just use mr squared to figure this out, okay? So there's a couple ways to do this. So the first way, and they may ask you to do this, is you have to use calculus, all right? So here's what we're going to do. Let's assume that the meter stick has a mass m and a length L, okay? Well, what we're going to do is we're going to split the meter stick up into a whole bunch of tiny, tiny little chunks. That little chunk is going to have a mass dm, okay? That means a differential mass. It means it's approaching zero, but not quite zero. Okay, so this little tiny chunk, okay? That little chunk is some radius r from our axis, all right? And what is the length of that chunk, okay? Well, we can do a ratio, okay? The mass over the length of the entire meter stick is going to be equal to dm over some distance, which we'll call dl. Okay, so we'll say the width of this little guy is dl, okay, for now. So basically we're saying the density of the meter stick is the same no matter how much of it I look at. The ratio of mass to length is going to be the same, okay? Now, for moment of inertia for extended objects, well, we had for point masses, we had this. We had the sum of the mr squareds, okay? Well, here's what you do if you have an extended object. You integrate, and we'll start with the r squared, and then you say dm. So what you're really doing is taking a whole bunch of infinitely small masses, finding each of their little teeny moments of inertia, and then you're adding them up, okay? Now, the problem here is you got two variables, r, okay? That goes from 0 to this distance there, L over 2, and you have dm. So these are two variables, and you have to get it down to 1. Well, if you look over here, we're pretty close. If you solve this little ratio for dm, you get m over L times dl. So we can rewrite this integral r squared times m over L dl, okay? Now, we're still not there yet. M and L are constants. That's the mass and the length of the entire meter stick. Radius varies, as we talked about a minute ago. And dl is a variable, okay? That length can be different depending on which dm you're looking at. So somehow I have to relate the radius to dl. Okay, well, here's the deal. So that dm has a width. So let's say here is the radius to the beginning of that dm, and here is the radius to the end of that dm. And let's just say, for the sake of argument, that dl is 1 millimeter, okay, just to make up a number. Then I hope you would agree that this radius and this radius, so the beginning and end of that dm, would be different by 1 millimeter, okay? The difference in the radius is dr, okay? That's dr means you're subtracting two radii, the final radius minus the initial radius. Well, if that's 1 millimeter, and I'm telling you that dl is 1 millimeter, then those two things are the same, all right? So we're going to make a substitution here. We're going to put r squared, and then we're going to integrate, or in here, instead of saying a dl, we're going to have a dr. Now, the one last and exceptionally important thing you need to do is you need to figure out what my limits of integration are, okay? What does the radius vary from? Well, the axis we define as 0, okay? My starting radius, the meter stick starts back here, which would be negative L over 2, and the meter stick ends over here, which would be positive L over 2. So those are my limits. You go from negative L over 2 to positive L over 2. If you don't have the right limits in there, you will get a nonsense answer. So you really have to think critically about that. All right, so what do we get? Moment of inertia. So if we integrate r squared dr, that's r cubed over 3. So you get r cubed over 3, and you still have this mass and this length in there. And you are evaluating this from negative L over 2 to positive L over 2. Those are the two radii you're plugging in here. So we get L over 2 cubed, okay, times m over 3L minus, and then negative L over 2 cubed m over 3L. Okay, now good news is some stuff will cancel here. We got L cubed over 8 times m all over 3L, and then minus negative L over 2 cubed is also negative, so it's negative L cubed over 8 times m all over 3L. All right, so one of these L's cancels, and this becomes a squared. Same thing here. This becomes a squared. And so you end up with an m and an L squared over, if you multiply top and bottom of each fraction by 8, you get a 24 in the denominator. And so you get 1 over 24 minus negative 1 over 24, which would be 2 over 24, which would be 1/12. So the moment of inertia of that meter stick is mL squared over 12. Okay. Now, by the way, there is a chart of these in the back of your book. Okay, so or in this chapter, I should say, there is a chart of these in the chapter, or you can look it up online too. So if you look up a rod, this would be a uniform rod, and find out what its moment of inertia is about its center of mass, you would see it's mL squared over 12, or 1/12 mL squared. Okay. Now, what if we change this up? What if we take that same rod and pivot it at its end? So you're swinging it like a baseball bat, let's say. All right. It's still got a mass m and a length L. Okay. Well, here's the good news. You don't have to redo all this work. It's still going to be, the moment of inertia is still going to be the integral of r squared m over L dr. Okay. What's going to change? Well, now your limits of integration change. The meter stick starts here at 0, and the meter stick ends at L. Okay, so you end up with the following. The moment of inertia about the end of the rod. Okay, so now we're holding it at the end. You still get your r cubed over, or times m over 3L, but now you're evaluating it, 3R, pardon me, which is, oh wait, pardon me, that is 3L. Let me go back. All right, that's an L. So you end up with, and you evaluate this from 0 to L. So you end up with L cubed times m over 3L. And one of the L's drops out, and you get mL squared over 3. Or you can write that as 1/3 mL squared. Now notice that's 4 times bigger than our first moment of inertia, meaning the meter stick is 4 times harder to spin it about its very end versus spinning it about its center. So a practical application of this is, let's say you are playing baseball or softball, and let's say you're having a hard time swinging the bat fast enough to hit the ball. So that's because maybe you were holding it right at the end of the bat. Well, they'll tell you to choke up on the bat a little bit, and therefore what you're doing is you're reducing the moment of inertia, making it easier to spin the bat and therefore hit the ball. Okay. Now, for this rod, you could pick any other axis you want to spin it around. So for instance, maybe you pick an axis here, which is, 1/4 L away from the end. Okay. Well, then your limits would be, this would become negative L over 4, and the rod would end at positive 3L over 4. So all you have to do if you're looking at a rod is just change the limits depending on where you pick your axis. All right, in the next video, we're going to talk about something that's incredibly important and useful, and often allows you to not have to integrate to find moments of inertia. And that's called the parallel axis theorem. So I will be talking about that in the next video. I hope this was helpful, and thank you very much.